So in the previous video we answered the question in which case there is solution for normal form systems. And of course the next question that we'll study how to solve such systems, how to find the solutions. And first we will concentrate on homogeneous systems. So the systems when we don't have this f of t vector function on the right. And for these systems, what can we say first? So the simple proposition is the following: if the vector function x1 of t is the solution of this system, and x2 of t and also xn of t are solutions of, we call it 1 of 1, then any linear combination of these solutions will be also a solution. Is also a solution. So if we can find some number of solutions of the system, we can combine them into linear combination to get another solution. This can be easily proved. Just substitute this one into the equation, and applying the linearity of derivative, we can prove this fact. Next thing that we will introduce, in fact, these homogeneous systems the theory for these systems very similar to the theory for second-order differential equations. And as you remember, we introduced the notion of linear independence and linear dependence for solutions. And the same thing we will do here. So let's introduce the following definition. The, let's say, m vectors, vector functions, let's say x1 and so on xm, these are vector functions, are said to be linearly dependent on some interval I if we can find the constants c1 and so on cn, which are not all zeros, such that, so we must say if there are constants such that the linear combination, sorry, it might be m, c1 x1 plus so on plus cm xm gives us zero vector. And these are functions, right? So in fact this vector function, they depend on t. And this must be held for any t from the interval. So if this is true for any t from the interval, then we say that these are linearly dependent. Otherwise the system is said to be linearly independent. So if we can find at least one point t for which this one is non-zero, this will be linearly independent. So, and let's now look at some examples. Example 1. So consider three vector functions. x1 of t is e of t, 0 e of t. x2 of t is 3e of t, 0, 3e of t. And x3 of t is t1, 0. So, and the question is, are these vector functions linearly dependent or not. And we can prove that these are indeed linearly dependent. Are linearly dependent since we can write 3 times x1 minus x2 plus 0 times x3 is 0. So there are numbers c1, which is 3, c2, which is minus 1, and c3, which is 0, so that we can write linear combination and get 0 for all t, right? So in fact, for any t from minus infinity to infinity, right? So these are linearly dependent. Let's look at another example. x1 of t is t and absolute value of t, and x2 of t is absolute value of t and t. And it's not really clear, it's not immediately clear that these are linearly dependent, so let's assume that this is true. So assume that x1 and x2 are linearly dependent. So we can find c1 x1 plus c2 x2 is 0. We can find c1 and c2 so that. Okay, let's see what does it mean. c1 times the vector t absolute value of t plus c2 times the vector absolute value of t. T must be 0 vector, which is 0, 0. So it means that the first component must be 0, the second component must be 0. So c1 t plus c2 absolute value of t is 0, and c1 absolute value of t plus c2 t also must be 0. This must be hold for any number t. So this must be true for any t from the given interval. And in fact here the interval is the same, minus infinity, infinity. So at least it must be true for t equals 1. So we can get that c1 plus c2 is 0, and for t equals minus 1, let's say, so we must get c1 minus c2 is 0, right? So we may get this system. And if you can solve this, you can see that the only solution is c1 is 0 and c2 is 0. So the only solution. So it means that the system is linearly independent, because we cannot find c1 and c2, which are non-zero, not all zeros, to get such combination. So it means that the system is x1 and x2 are linearly independent. Okay. The following importance theorem holds for the general solution of homogeneous system. This theorem is similar to the theorem for second order homogeneous linear differential equations. So if x1 and so on xn are linearly independent solutions of the system, so the system is this one, homogeneous one, on some interval I, then the general solution of this system is linear combination of these linearly independent solutions. So this theorem gives us the form of general solution of the system. Let me remind you that general solution is a solution which can be applied to solve any initial value problem. So, how to find general solution of the system? We need to find the set of n linearly independent solutions of the system. Let me also introduce some notations. So the set x1 and so on xn is said to be the fundamental solution set. So this is fundamental solution set. And also using this set, we can write a matrix x of t, which consists of these solutions as columns. So if one solution, of course, this is a vector function of length n. So let's say the first solution has the components x11 and so on xn1, and the second one has the components x12 and so on xn2, and so on. We have n's, sorry, it should be 1n, and solution has components x1n and so on xnn. Then this capital X is the following matrix, and the name of this is fundamental. Okay, sorry. Fundamental matrix. Let's consider the following example. Verify that this given set of vector functions is fundamental solution set for this system on the interval minus infinity to infinity. Find the fundamental matrix and general solution. So the first step, let's verify that this is fundamental solution set. So to do this, the first step, fundamental solution set means two things: that the set is the set of solutions so we must check each vector here that this is indeed solution of this system. Let's do this. So for the vector, let's say x1 of t is e to t, e to t, and e to t. So the first vector here. x1 prime of t is 2e to t, 2e to t, and 2e to t. So this is the derivative. So we know the left hand side, and let's calculate the right hand side. 0, 1, 1, 1, 0, 1, 1, 1, 0 times the vector x, which is e to t, e to t, e to t. So what do we get? This row times this one, we get e to t plus e to t, which is 2e to t. The second row, e to t 0 plus e to t, again 2e to t. And the third row, e to t plus e to t, again 2e to t. So indeed these two things are equal, so x1 satisfies the system. Let's also do the same thing for x2. So x2 of t is, so this is the vector minus e to the minus t, 0, e to the minus t. And we must check this for the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0. 0, 1, 1, 1, 0, 1, 1, 1, 0. So we must check that this satisfies the system like this. So first let's find x2 prime of t, which is derivative of this one is minus, and this minus will be plus e to the minus t. Derivative of 0 is 0, and derivative of this one is minus e to the minus t. And let's calculate the right hand side of the system. So here we write the vector, and so what do we get? The first row times this thing will be e to the minus t. This one times this one, so we see 1 times minus e to the minus t. 0 times 0, 1 times e to the minus t will be 0. And this one times this one will give only 1 times minus e to the minus t, and the rest things are 0, so this is minus e to the minus t. And indeed we have equality here, so x2 also satisfy the system. Okay, let's look at x3, which is 0 e to the minus t minus e to the minus t. So x3 prime is 0 minus e to the minus t and e to the minus t with plus. And let's find the right hand side of this system. So multiply the first row by this thing will give us 0. This one times this one will be minus e to the minus t, and this one times this one will give us e to the minus t. So indeed the same thing, so x3 also satisfies the system. Okay, great. So we know that all these three vectors satisfy the system. So we know that these are solutions. The next question is, are they linearly independent solutions? So let's answer this question. So are they linearly independent? So, and we first assume that they are linearly dependent. That they are linearly dependent. And what does it mean? It means that for any there are C1, C2, C3 such that C1 times e to the 2t, e to the 2t, e to the 2t plus C2 times minus e to the minus t, 0 e to the minus t plus C3 times 0 e to the minus t minus e to the minus t. This is 0, and not all C1, C2, C3 are zeros. And this must be held for all t from minus infinity to infinity. So in particular, this is true for, let's say, t is 0. Just take the simplest case, t is 0. This is one of the points of this interval. So it means that C1 times the vector 1, 1, 1 plus C2 times the vector minus 1, 0, 1 plus C3 times the vector 0, 1, minus 1 is 0. or we get the system C1 minus C2 must be 0. This is 0 vector, right? So 0 vector here. So the component wise they must be equal, plus C3 must be 0, and C1 plus C2 minus C3 must be 0. So what we can get from this, the first thing that we can do to solve the system, to find C1, C2, C3, we can calculate the determinant of the matrix of the system. It's 1 minus 1, 0, 1, 0, 1, and 1, 1, minus 1. So the determinant is 0, minus 1, plus 0, minus 0, plus 1, minus 1. So it's non-zero. So it means that the system has unique solution which is C1 is C2 is C3 is 0. So there are no non-zero numbers like this. It means that they cannot be linearly dependent, right? So it means that they are linearly independent. Okay, so what we indeed proved, we proved this part, that this is fundamental solution set. We proved that these three vectors are solutions of the system, and these three vectors are linearly independent. And what else do we need? We need to find fundamental matrix and general solution. So the fundamental matrix is capital of T is just matrix which is combined from the columns are these vectors which are solutions. This is fundamental matrix, and the general solution is small x of t. This is C1 times the first vector e to the 2t, e to the 2t, e to the 2t, plus C2 times the second vector minus e to the minus t0, e to the minus t, and plus C3 times the third vector 0, e to the minus t, minus e to the minus t. In fact, another way to write this, that small t is capital X of t times vector c, where vector c is the column vector C1, C2, C3.